All right, everyone. Hello and welcome to the... I don't know if the subtitles are working. Hopefully the subtitles are working. Maybe. We're trying out technology. So welcome back to Applications of Derivatives. So what we're going to be looking at for this first section here is really diving deep into what does the first derivative tell us about the graph of a function. So we're going to start off with a little bit of a recap of what you have learned before about the relationship between the sign of the derivative and the behavior of the function. So if the first derivative is positive for points on a particular interval, then the function is increasing on that interval. And if the first derivative is negative on a particular interval, then the function is decreasing on that interval. So if the derivative is positive, then the function is increasing on the interval from a to b. If the first derivative is negative on all the points in an interval a to b, then f is decreasing. And if the derivative is equal to 0 for all of the points on a particular interval, not just one, all of them, then you have a constant on that interval. So for these next two problems, what we're going to do is we're not going to look at the graph. We're going to, without a graph, figure out the intervals on which this function is increasing and the intervals on which this function is decreasing. And all we need for this is the first derivative and the sign of the first derivative. So let's actually take the first derivative of x times e to the power of negative x. Now, since this is times, this is going to involve the product rule, and the second part of the product is e to the negative x. So since e to the negative x is a composition of functions, we will need chain rule, and we're only going to need chain rule for the derivative of the second part of the product. So let's start with the derivative of the first part of the product. Derivative of x is 1 times the second part of the product left alone, e to the negative x. Then we're going to add to it the first part of the product left alone, x, times derivative of the second part of the product. Now the derivative of e to the negative x, the outside function is the exponential of base e, the inside function is negative x. So the derivative of the outside is e to the negative x, times derivative of the inside, derivative of negative 1x is negative 1. So what we're going to start with is figuring out where the derivative could change signs. Where could increasing and decreasing switch? And to figure that out, what we're going to do is we're going to find the critical points. The critical points occur where either the first derivative equals 0 or where the first derivative is undefined. So I'm going to take this function here and I'm going to do a little bit of simplifying, and I'm going to figure out where this derivative equals 0 and where this derivative is undefined. Now on either side of that plus sign in the middle, there is a common factor of e to the negative x, so I am going to factor out e to the negative x out of both terms. So what's left over in that first term is 1, and then positive times a negative is a negative, and then what's left over in the second term is x. Then if you want to turn a negative exponent into a positive, you can do so by moving it into the denominator. So because there is multiplication right here, I'm going to take this e to the power of negative x, and I am going to move it into the denominator to become e to the power of positive x. And then left over in the numerator is 1 minus x. So obviously, our derivative is a fraction that contains variables in the denominator. So a fraction is equal to 0 when the numerator, 1 minus x, equals 0. So this derivative is equal to 0 when x is equal to positive 1. A fraction is undefined when the denominator, e to the power of x, equals 0. Now, e to the power of x is never actually going to give us 0. An exponential function is never equal to 0, so it's not undefined anywhere. So that just leaves us with one single critical point, x equals 1. So x equals 1 is the only place where the derivative could change signs from positive to negative or negative to positive. Because x equals 1 is our only critical point, this is the only point where increasing and decreasing could switch. We don't know if they're going to, but x equals 1 is the only place where it could switch. And since x equals 1 is the only point where the derivative equals 0, what that also means is that everywhere else, the derivative is either going to be positive or the derivative is going to be negative. It's either going to be one or the other, and x equals 1 is the only point where it equals 0. So here's what I'm going to do. I'm going to take the domain of the derivative. Now the domain of f prime here is going to be all real numbers, so negative infinity is on this side, positive infinity is on this side. And I basically drew a number line to represent the domain of the first derivative. And what I'm going to do is I'm going to put my critical point 1 on this number line. So what I've done is I've broken up the domain of the first derivative into two separate subintervals. We have the subinterval from negative infinity to 1, and then the interval from 1 to infinity. And remember, x equals 1 is the only place where the derivative is equal to 0, which means everywhere else the derivative is either going to be positive or the derivative is going to be negative. So here's what I'm going to do. I'm going to take each of my intervals and I'm going to pick a test point in each of them. And I'm going to plug that test point into the first derivative. And all I really care about is whether the derivative is positive or whether the derivative is negative. Now, since it's either going to be one or the other, it really doesn't matter which test point you pick. You could pick any test point in that interval, and you're either going to get a positive number or you're going to get a negative number. Don't pick one because you're just going to get 0, and that doesn't really tell you anything. So pick a test point that's not 1. So we're going to test, let's say, 0. And I'm going to plug 0 into the first derivative, and all I really care about is whether it is positive or negative. So I get 1 minus 0 divided by e to the 0 is a positive number. Now, since my test point came out positive, that means all of the derivatives are positive on this interval. No matter what test point you pick, all the derivatives are positive. Then what I'm going to do is I'm going to pick another test point, this time in the interval from 1 to infinity. Again, doesn't really matter what you pick. Pick a point that's easy to work with. Let's say 2. And I'm going to plug 2 into the first derivative, and all I really care about is whether the derivative is positive or negative. So if you plug in 2, you get 1 minus 2 over e squared, which is a negative number. So since our test point came out negative, that means all of the first derivatives are negative on this interval. Remember, if the first derivative is positive, that means the function is increasing. And if the first derivative is negative, that means the function is decreasing. So let's actually write out our intervals of increasing and decreasing. So this derivative is going to be, the derivative is positive on the interval from negative infinity to 1, which means that the function is increasing on the interval from negative infinity to 1. Now, whether they get parentheses or brackets, infinity is not a number. It should always get a parenthesis. And remember, at 1, it is neither increasing nor decreasing. So I'm also going to give this a parenthesis as well. Then the function is going to be decreasing where the derivative was negative. So since the derivative was negative on the interval from 1 to infinity, that means the function is decreasing on the interval from 1 to infinity. Infinity gets a parenthesis, and once again, positive 1 gets a parenthesis. So then we're going to do the same thing for the next one. So we're going to take 2x cubed plus 3x squared plus 1, and we're not going to use a graph. We're just going to use the first derivative and figure out where is this function increasing and decreasing just based on the sign of the derivative. So let's actually find the first derivative. So derivative of 2x cubed is going to be 6x squared. Derivative of 3x squared is plus 6x, and the derivative of 1 is 0. So I'm going to start by finding the critical points. The critical points occur where the first derivative is either equal to 0 or where the first derivative is undefined. I also don't know what is going on with the random crossing off it's doing. I don't know what's up with that. I'm very sorry. All right, so let's take the first derivative, 6x squared plus 6x. Let's set it equal to 0 and let's solve for x. So there's a common factor here of 6x. Gives us x plus 1 for the leftovers. And we get two critical points. One of them is x equals 0, and the other one is x equals -1. So we have two critical points. So we're going to do the same thing that we did last time. And these are the only two critical points that we have to worry about. The derivative is a polynomial. It's not undefined anywhere. So all we had to worry about was where the derivative was equal to 0. So once again, I'm going to draw a number line with -infinity on this side and +infinity on this side. And remember, this number line is going to represent the first derivative. And I'm going to put my two critical points in numeric order on the number line, so -1 over here and 0 over here. And what that has done is that has broken up the domain of the first derivative into three separate intervals. The interval from -infinity to -1, the interval from -1 to 0, and the interval from 0 to infinity. And what I'm going to do is I'm going to once again pick a test point in all three of these intervals, and it doesn't really matter what test point you pick. All that matters is whether the derivative is positive or the derivative is negative. So a good test point to pick between -infinity and -1 is, let's say, -2. So let's plug -2 into the first derivative. Factored, unfactored, doesn't really matter. And we're going to see whether that comes out to a positive number or a negative number. So we get 6 times -2 times -2 plus 1 is a positive number. So since our test point came out positive, that means the first derivatives are positive on this interval. Next, yes, we do have to pick a test point between -1 and 0. We are going to have to pick a fraction. You have a calculator, so it's not going to be that big of a deal. So let's plug in -1/2, and we're going to plug in -1/2 into the first derivative. So 6 times -1/2 times -1/2 plus 1 is going to be a negative number. So since our test point came out negative, that means the derivatives are negative on this interval. Then we're going to pick a test point in our last interval from 0 to infinity. So let's pick +1. Remember, we don't want to pick 0 and we don't want to pick -1. We want to pick test points that are not the critical points. Let's pick 1. And we're going to plug 1 into the first derivative. And if you plug 1 into the first derivative, it is definitely a positive number. So since our test point came out positive, that means all of the first derivatives are positive for this entire interval. So if the first derivative is positive, that means the function is increasing. So the function is increasing here, and it is increasing here. And if the first derivative is negative, the function is decreasing. So the function is decreasing right here. So let's wrap all of this up into our intervals of increasing and decreasing, and let's actually use interval notation. So this function is increasing on two intervals. One interval is between -infinity and -1. And remember, it is neither increasing nor decreasing at -1, so I'm going to give it a parenthesis. And it is increasing again on the interval from 0 to infinity. Then it is going to be decreasing. I don't know what is going on with this. I am so sorry. There we go. It's a little more legible. It is decreasing on the interval from -1 to 0. Now, just going back a second, and I'm going to change colors for this. Let's see. Let's pick blue. Now, at -1 here, remember, that was a critical point. The function went from increasing to decreasing here at -1. So that point right there, where the derivative equaled 0, where the derivative changed signs from positive to negative. That's a local maximum. There is a local maximum at x equals -1. And then over here at 0, the function went from decreasing to increasing. So right there, that's a local minimum. Oh my God, I don't know what is going on. There is a local minimum at x equals 0. Now, using the sign of the first derivative to determine whether these are local minimums or maximums is actually something called the first derivative test. And you do have to know this one because you will be using this one all the time. You are going to be using first derivative test a lot. So let's actually go through it and let's see what the first derivative test says. So you have your critical point C. Now, if your first derivative changes signs from positive to negative, that means the function will be switching from increasing to decreasing. That means you have a local maximum there at your critical point. Now, if the first derivative changes signs from negative to positive, that means the function is going from decreasing to increasing. That means you have a local minimum. So right away, just looking at what the sign of the first derivative is on either side of your critical point could tell you whether you have a local max or a local min. Now, your first derivative is not going to always change signs on either side of your critical point. If that happens, if your first derivative does not change signs on either side of your critical point, there is no local extrema at x equals c. Means you have one of these two situations. The derivative goes from positive to positive. That is not a min or a max. Or the derivative goes from negative to negative, which means that is also not a minimum or a maximum. So definitely know the first derivative test. You will be using it a lot. And notice its name, first derivative test. There is going to be another test called the second derivative test, which will use the second derivative to classify critical points as minimums or maximums. We're going to get to that later. So just pay attention to which test you're using. Which derivative are you using, the first derivative or the second derivative? So for this next one, we're going to use calculus, i.e. we're going to use derivatives, to find all of the local extrema of f of x equals x cubed minus 12x minus 5, and we're going to state whether they are local minimums, local maximums, or maybe neither, and we're going to justify your answer means please state what test you used. So the first step that we're going to do is we're going to find where the local extrema could occur. Local extrema always occur at critical points. The first step that we're going to do is we are going to find the critical points. Now, critical points occur where either the first derivative equals 0 or where the first derivative is undefined. So let's start with finding the first derivative. So f prime of x is going to equal 3x squared minus 12. Since this is a polynomial, we don't have to worry about where the derivative is undefined, but we are just going to take the derivative. We're going to set it equal to 0, and we're going to solve for x. So if you add 12 to both sides and divide both sides by 3, you get x squared equals 4. Gives us two critical points. X equals -2, and x equals +2. So remember, these are the critical points. These are where the local minimums and maximums could occur. Not every critical point is a local min or max. So right now, we don't have enough information to say, yeah, this is a min, this is a max. We don't know. We just know that these are 2 points where the derivative equals 0. To actually figure out what these are, what we're going to have to do is we're going to have to look at the sign of the first derivative on either side of these critical points, and then we'll be able to tell if they're minimums, maximums, or neither. So I'm going to draw a number line. We have negative infinity on this side, and we have positive infinity on this side. And since we are going to eventually be working with second derivatives, I'm going to make sure that I label this as the first derivative. And I'm going to put each of my critical points on the number line. So starting with negative 2 over here and positive 2 over here. And what I'm going to do is we have now broken this up into 3 separate intervals. We have the interval from negative infinity to negative 2, then the interval from negative 2 to 2, then the interval from 2 to infinity. And I'm going to pick a test point in each of these intervals, and I'm going to plug that test point into the first derivative. Remember, doesn't matter what test point you pick. Any test point in these intervals, don't use negative 2 or 2, use something else. Any test points in these intervals are going to work, and all you really care about is whether the derivative is positive or negative. So let's pick a test point less than negative 2, let's say negative 3, and we're going to plug negative 3 into the first derivative. So if we plug negative 3 into the first derivative, we get 3 times, negative 3 squared minus 12, which is a positive number. Since the test point came out positive, that means all of the first derivatives are positive on this entire interval. Next, let's pick a test point in the interval from negative 2 to 2. Let's say 0. 0 is a great test point to use between a negative number and a positive number. And we're going to plug 0 into the first derivative, so we have 3 times 0 squared minus 12, which is obviously a negative number. So since our test point came out negative, that means all of the first derivatives are going to be negative for this entire interval. Then we're going to pick a test point on this interval from 2 to infinity. So let's say 2. And we're going to plug it into the first derivative, so 3 times 2 squared. Sorry, we're going to pick x equals 3. Sorry, I got distracted by whatever my pen is doing. Let's pick x equals 3 for a test point, and we're going to plug 3 into the first derivative. So we have 3 times 3 squared minus 12 is a positive number. Don't do what I just did. Don't pick the critical point itself. Pick a point that's greater. And since that test point came out positive, that means the first derivative is going to be positive for every point on this interval. So, going from here, now that we know what the sign of the first derivative is on either side of our critical points, we can actually classify our critical points as local mins, maxes, or neither. So remember, if the first derivative is positive on a particular interval, the function is increasing. If the first derivative is negative on a particular interval, the function is decreasing. So on either side of negative 2, the function goes from increasing to decreasing. So that point right there, that's a local maximum. So there is a local maximum. At x equals negative 2. Then over here at 2, the function went from decreasing to increasing, which means right there, that's a local minimum. So there is a local minimum at x equals positive 2. Now, there is going to be more than one test for this, and we are going to state what test we used. Since we used first derivatives to figure this out, we used the first derivative test. So by the first derivative test, and FDT is a completely acceptable shorthand. I know exactly what FDT is and what it stands for, so you can use FDT. So we're going to take this next one, and we're basically going to do the same thing. We're going to use calculus, using derivatives, to figure out where the intervals on which f is increasing and decreasing. And at the same time, we're going to identify the local extrema, meaning we're going to figure out whether these critical points are minimums or maximums. So first thing I'm going to do is I'm actually going to find the first derivative. So taking the first derivative is 12x cubed minus 12x squared minus 12x plus 12. And then to find the critical points occur where either the first derivative equals 0 or where the first derivative is undefined. So since this is a polynomial, we don't have to worry about where the derivative is undefined. All we have to worry about is where the derivative equals 0. So first thing I'm going to do is I'm going to factor out a 12, make my numbers a little more manageable. So we have x cubed minus x squared minus x plus 1. We're going to set it equal to 0. And we're going to solve for x. Now, I am going to factor this. This polynomial involves 4 terms, so this is going to involve a process called factoring by grouping. If you don't remember what factoring by grouping is, here's a recap. So I'm going to split this up into 2 groups of 2. I'm going to put the first 2 terms into a group and the last 2 terms into a group. And what I'm going to do is I'm going to take the GCF out of each group. So the greatest common factor between x cubed and minus x squared is going to be x squared. Gives us x minus 1. Then I'm going to take the greatest common factor out of the second groups. There is no GCF between negative x and plus 1 other than 1. However, since that x is negative, I am going to factor out a negative 1. So negative x divided by negative 1 is positive 1x. Positive 1 divided by negative 1 is minus 1. Then on either side of that central minus sign, there is an x minus 1 in common, so I'm going to factor that out. And I'm going to put the leftovers in parentheses. So when I remove an x minus 1 out of this first group, I have an x squared left over. Then when I remove an x minus 1 out of the second group, I have a minus 1 left over. Now x squared minus 1 can be factored. That is a difference of squares, so I'm going to factor it as a difference of squares. So x squared minus 1 is going to factor as x minus 1 times x plus 1. And remember, the whole point of this is so that we could set it equal to 0 and solve for x. So 12 never equals 0. So 12 has nothing to do with the critical points. Then when we take x minus 1 and set it equal to 0, we get a critical point of x equals 1. And it really doesn't matter that this factor occurred twice, and so it really doesn't matter that this has multiplicity. X equals 1 is a critical point, and that's it. We're going to move on. Then when we take x plus 1 and set it equal to 0, we get another point of x equals negative 1. So these are the 2 critical points. These are the only points where increasing and decreasing could switch. These are the only points where minimums and maximums could occur. Without more information, we don't know any of that. We don't know whether these are minimums, maximums, or neither. So what we're going to have to do is we're going to have to look at the sign of the first derivative on either side of our critical points. So this number line is going to represent the first derivative with positive infinity on this side and negative infinity on this side. Then I'm going to put my 2 critical points on my number line. So I have negative 1 there and positive 1 there. And I'm going to pick test points in each of these intervals, and I'm going to see whether the first derivative is positive or negative at these test points. Don't pick negative 1 and 1. That'll just give you 0. Pick other points. So a good test point to use in the interval between negative infinity and negative 1 is, let's say, negative 2. So I'm going to plug negative 2 into the first derivative and see whether I get a negative number or a positive number. Factored, unfactored, doesn't really matter. So 12 times negative 2 minus 1 times negative 2 minus 1 times negative 2 plus 1 is a negative number. So since my test point came out negative, that means the first derivative is negative on this entire interval. Next, we're going to pick a test point between negative 1 and 1. A good test point to use between a negative number and a positive number is 0. So I'm going to take 0 and I'm going to plug it into the first derivative. So we have 12 times 0 minus 1 times 0 minus 1 times 0 plus 1 is a positive number. So since our test point came out positive, the first derivative is positive. Now, here's a trap that a lot of students fall into. Do not assume that the derivative will be negative on the next interval. You do have to pick a test point. You do have to take 30 seconds to evaluate it at the derivative at that point. because the first derivative is not always going to change signs on either side of your critical points. Here's a demonstration. A test point between 1 and infinity that you could pick is 2, and we're going to evaluate the first derivative at 2. And when you plug in 2 into the first derivative, you get a positive number. So the derivative did not change signs on either side of 1. That's actually going to be really important. Now, let's go with the increasing and decreasing first. Remember, if the derivative is positive, the function is increasing. So it is increasing on this interval here and this interval here. So it is actually increasing on 2 separate intervals. And no, you cannot combine them. You cannot combine this as -1 to infinity, because here at 1, remember, 1 is a critical point. It's neither increasing nor decreasing at 1. So no, you can't just lump it together. You cannot just lump this all together into -1 to infinity. You have to list this as 2 separate intervals. So the first interval it's increasing on is the interval from -1 to 1. Then it is also increasing on the interval from 1 to infinity. Do not lump those together, because at 1, it's not increasing. Then this function is going to decrease wherever the derivative is negative. So this function is decreasing on just this interval here from -infinity to -1. So it is decreasing on the interval from -infinity to -1. So while we're at it, we can also identify whether these critical points are local minimums, local maximums, or possibly neither. So let's start with -1. This function went from decreasing to increasing here at -1. So that is obviously a local minimum. So there is a local minimum at the point x equals -1. Now, here at 1, the function went from increasing to increasing. That is not a minimum or a maximum. So x equals 1 is neither a local minimum nor a local maximum. It's one of those, what we're informally calling saddle points for now. So x equals 1 is not a local extrema. It is neither a minimum nor a maximum. So then for this last one, we're going to use derivatives using calculus. We're going to identify the local extrema of this function here. Now, you might recognize this function. We use this exact same function in 4.1, so we're just going to use the derivative that we found back in section 4.1. If you don't remember this, go back and rewatch the section 4.1 video where we find and simplify this derivative. So when we found the first derivative, we found this to be 4 minus 5x all over 3x to the power of 1/3. So to find the local minimums or maximums, you need to start with finding the critical points. The critical points are going to occur where the first derivative is either equal to 0 or where the first derivative is undefined. And since this has variables in the denominator, we do have to worry about the possibility that the first derivative is undefined. So the first derivative is equal to 0 when the numerator, 4 minus 5x, is equal to 0. A fraction is equal to 0 when the numerator equals 0. So if you solve for x, you get x equals 4/5. Then a fraction is undefined when the denominator equals 0. So the first derivative is undefined when the denominator, 3x to the power of 1/3, equals 0. And when you solve this for x, you get x equals 0 as your other critical point. So there are two critical points. We have 4/5 and we have 0. We don't know if these are minimums or maximums. In order to figure out whether they're minimums or maximums or neither, you do have to look at the sign of the first derivative on either side of your critical points. So I'm going to draw another number line. This number line is going to represent the first derivative with positive infinity over here and negative infinity over here. And I'm going to put my two critical points in numeric order on my number line. So I have 0 first and then 4/5. Then I'm going to pick a test point in each of these intervals, and I'm going to plug that test point into the first derivative, and all I really care about is whether it is positive or negative. Don't pick the critical points themselves, pick something else. So a good test point to use on negative infinity to 0 is, let's say, -1. So I'm going to plug -1 into the first derivative. So you have 4 minus 5 times -1 over 3 times -1 to the power of 1/3 gives us a negative number. So since our test point came out negative, that means the first derivative is negative on this entire interval. Then we've got the interval between 0 and 4/5, and we're going to pick a test point between 0 and 4/5. Let's pick 1/2. So we're going to take 1/2 and we're going to plug it into the first derivative, and we're going to see whether this is positive or negative. So 4 minus 5 times 1/2 divided by 3 times 1/2 to the 1/3 is going to be a positive number. Since our test point came out positive, that means our derivatives are positive for that entire interval. Then we're going to pick a test point between 4/5 and infinity. So a good test point that's greater than 4/5 is, let's say, 1. So let's take 1 and let's plug it into the first derivative. So 4 minus 5 divided by 3 is a negative number. Since our test point is negative, that means all of the first derivatives are negative for this entire interval. All right, so if the first derivative is negative, the function is decreasing. If the first derivative is positive, that means the function is increasing, and then the function goes back to decreasing again here. So for our local extrema, I'm going to switch colors again. Let's start with 0. So on either side of 0, the function went from decreasing to increasing. So what is that? That is a local minimum. So there is a local minimum at x equals 0. Then here at 4/5, the function went from increasing to decreasing. So here at 4/5, that is a local maximum. So there is a local max at x equals 4/5. Remember, do not assume that the derivative will always change signs. You do need to plug in the test point, and you do need to see whether the derivative actually does change signs. Okay, so thank you all very much for watching. I hope that this video was helpful, and if you have any questions, please feel free to send me an email, and I will do my best to answer your questions. So thank you for watching, and I will see you guys in the next section.